This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to the discussion. Today, we're delving into a research paper outlining a methodology for statistically analyzing factors influencing 3D object detection performance in autonomous driving. The authors propose a novel approach to understanding and mitigating errors in these crucial systems. What are the core challenges addressed by this methodology, and why is this important for the field?
The primary challenge is the black box nature of deep learning list object detectors. Their high accuracy often masks underlying vulnerabilities. Understanding which environmental or object-specific factors significantly impact detection accuracy is crucial for ensuring the safety and reliability of autonomous vehicles. This methodology aims to provide a systematic and statistically rigorous way to identify these weaknesses. The importance lies in moving beyond simple performance metrics to a deeper understanding of error sources.
The paper mentions using the NewScenes dataset. Why was this dataset chosen, and what are its key characteristics that make it suitable for this type of analysis?
NewScenes was selected due to its multimodal nature, LiDAR and cameras, high data volume, and rich annotations. The diversity in scenarios, day-night, weather conditions, locations, and the detailed object annotations, including attributes like whether a car is parked or moving, are essential for a comprehensive statistical analysis. The availability of both LiDAR and camera data allows for a comparison of how different sensor modalities are affected by various factors.
The methodology employs univariate mutual information, MI. Why was MI chosen as the primary statistical measure, and how does it address the challenges of mixed data types, categorical and numerical?
MI was chosen because it measures the mutual dependence between two variables, regardless of whether the relationship is linear or nonlinear. This is crucial because the influence of factors on detection performance might not be straightforward. To handle mixed data, a nearest neighbor entropy estimator is used for numerical variables, which avoids the information loss associated with discretization methods. The choice of K3 minimizes random error while keeping systematic error negligible.
The paper analyzes several object detectors, MONODO, FCOS3D, POINT, PILLARS, and MIGZE. What are the key architectural differences between these detectors, and how does this influence the interpretation of the results?
The detectors represent different architectures within camera-based, MONODIS, FCOS3D, and LiDAR-based, POINT, PILLARS, MEGVE, object detection. MONODIS and FCS3D are monocular, using a single camera image, while POINT, PILLARS, and MEGVE are voxel-based, processing point cloud data from LiDAR. Comparing results across these architectures helps understand how sensor modality interacts with the influence of various factors. The similar architectures within each sensor type help isolate the effects of the sensor itself.
The results highlight the strong influence of bounding box parameters, size, yaw angle, volume, on detection performance. Can you elaborate on why these factors are so influential and what implications this has for detector design and testing?
The size and orientation of the bounding box directly relate to the object's apparent size and pose in the sensor data. Smaller or poorly oriented objects are inherently harder to detect, regardless of the detector architecture. This highlights the need for detectors robust to variations in object size and pose, and for test catalogs that include a wide range of these parameters. The strong influence of volume, in particular, suggests that the overall size of the object is a critical factor.
The paper also investigates class-specific differences, particularly between car and pedestrian detection. What are the key findings regarding these differences, and how do they relate to the sensor modalities?
For cars, bounding box parameters remain dominant. However, for pedestrians, the attribute, moving, standing, sitting, lying, becomes significantly more influential for LiDAR-based detectors. This suggests that LiDAR's performance is more sensitive to the pedestrian's pose, likely due to variations in point cloud density and reflectivity based on pose. Camera-based detectors show less sensitivity to the attribute, indicating a difference in how the two sensor modalities capture and represent pedestrian information.
The discussion of distance as a factor is interesting. How do the results regarding distance differ between LiDAR and camera-based detectors, and what are the potential reasons for these differences?
Camera-based detectors show a more significant drop in recall at longer distances compared to LiDAR. This likely reflects differences in the effective range of the sensors in the new scene's dataset. LiDAR generally has a longer range, allowing for more reliable detection of distant objects. This highlights the importance of considering sensor limitations when designing and evaluating object detection systems.
The paper mentions the surprisingly low influence of rain. How can this be interpreted, and what are the limitations of the dataset that might contribute to this finding?
The low influence of rain might be due to the relatively low intensity of rain events in the new scenes dataset. The dataset doesn't provide detailed rain intensity information, which is a limitation. Other studies have shown a significant negative impact of rain on both camera and LiDAR-based detection, suggesting that the new scenes data might not fully capture the effects of heavy rain.
The methodology focuses on false negatives, FN. Why was the focus limited to FNs, and what are the implications of not considering false positives, FPs?
The focus on FNs allows for a more direct analysis of the influence of object and environmental factors. FPs, ghost detections, are more challenging to analyze in relation to specific object or environmental characteristics. While ignoring FPs is a limitation, the analysis of FNs provides valuable insights into the factors that cause missed detections.
The paper suggests several avenues for future research. What are some of those promising directions, and how could these extensions improve the methodology?
Future work could involve a more detailed analysis of localization and classification errors separately, using metrics like IOU, including a detailed analysis of FPs, potentially using environment-specific meta-information, would provide a more complete picture. Multivariate analysis could reveal interactions between factors, and using explainable AI techniques could help pinpoint the causal mechanisms behind detection errors.
The use of a univariate analysis while providing a ranking of influence doesn't capture interdependencies between factors. How could this limitation be addressed in future work?
The limitation of univariate analysis in capturing interdependencies between factors can be addressed by employing multivariate analysis techniques. Methods like partial correlation analysis or conditional mutual information could be used to assess the influence of one factor while controlling for the effects of others. This would provide a more nuanced understanding of the complex interplay between various factors.
The paper relies on the new scenes validation set. What are the implications of not using the test set, and how might this affect the generalizability of the findings?
Using only the validation set means the results might reflect overfitting to the specific characteristics of that set. The test set, unseen during model training, would provide a more robust evaluation of the detector's performance and the generalizability of the findings. Systematic errors due to training could be better identified using the test set.
In summary, this paper provides a valuable methodology for systematically analyzing the factors influencing 3D object detection performance. The findings highlight the importance of considering object size, pose, and sensor limitations, particularly in the context of autonomous driving. Thank you for this insightful discussion.